Okay. Good morning, students. My sincere apologies. We started now 15 minutes late because I had some serious hardware problems here. At 8 o'clock things were not working, so I had to do a quick fix. And it looks as if we are up and running. Everything. I'm getting more viewers. Of course, don't worry. Everything will be recorded and written down, and we have the book, of course. But again, sorry for you have to wait this time. Kind of a panic. Okay. Today's topic is rolling contact and non-holonomic constraint. It's chapter 16 of the book. And usually Jason Moore is following the chat, but he's on a holiday. He's cycling with his wife through the Netherlands currently. Beautiful weather, so that works fine. So I will try to look at the chat, but don't expect too much of the chat. So if you have questions, please collect them, keep them for the questions and answers after this 1 hour lecture in the Zoom session, which is of course also then late 15 minutes. Okay, rolling contact and non-holonomic constraints. Well, one thing, the first part is very clear, right? Rolling contact. So picture a wheel which rolls without slip. Yeah. Rolls without slip. That's usually what you want from a wheel, right? And we take the general case. So in a three-dimensional world, you have some contact point here where the wheel is, and this is the wheel, and then the wheel is moving forward with some velocity. The wheel has also some radius, and of course it then also has some angular velocity here, or you could say that's the vector. You could also say like this, has some omega, and we know of course that what is it? Omega is v divided by r or something like that, and then this with the ground, this is what we call the contact point, and that is what the whole thing is about. That in this contact point we have no slip. That is the idea, and that connects actually this forward velocity with the rotational velocity. And of course the wheel can also tilt, but for now we only look at we look at an upright wheel. So so you could say a 2D, because so if we do a top view of that, so we say top view, then what do you get? Well, I had this as x, y, and this as z. So in a top view, for an upright wheel, we have our coordinate system x and y here, with the origin. And then somewhere the wheel is pointing in some direction. We have a contact point. The wheel has some dimensions, right? Some radius. And this is to show that here's the axle. So this is this contact point. It's perfectly upright. Later on in the course we will do 3D dynamics, and then we will go to wheels in a three-dimensional space. But for now we do the simple two-dimensional. So the wheel, well, which is usually the case in cars and bicycles. There's not so much leaning going on. So in the first approximation that's pretty good. So here we go to a two-dimensional world. Okay, then, well, like any rigid body, of course, it has a position on the plane, and it has, of course, makes an angle, phi, with the horizontal, with the x-axis. Of course, it has a radius r, and then on top of that, we have to make sure that it doesn't slip. So it shouldn't slip in this direction, sideways, but it also shouldn't slip in that direction, meaning that not only do we have a coordinate for the position and the angle, but we also have to need some coordinate to denote the angular velocity about the axis. So that's beta dot, we call that beta So note suddenly we have like a mixture. It's like a sort of a 2.5D we're now creating. Due to this we get 2.5D. Because, well, not only do we have now the coordinates, the xi being the x, the y and the phi, but we also have this beta angle. So that's what we say, that's the half D. Okay, let me get this out of the way because I need a bit space there. Now, what does that mean, there is no slip? It means that in this point there can be no sideway velocity. So if we draw the velocity vector, and just like we draw the velocity vector, something like this. So this is the velocity vector, or in other words, this is x dot and y dot. Then we can decompose this velocity vector in a part which is along the direction of travel, which we call v along, right? And then there's also a part which is perpendicular to the one, and that is what we will call v perpendicular. And now we want, of course, that this v perpendicular is 0 and that the v along the line complies with the rotational speed and with the radius, like we had here, omega is v over r. Okay, so no side slip, we call that side slip. That means that this v perpendicular is 0. And you could also say pure rolling in the forward direction. In forward direction means actually that this v in that direction should be equal to this beta dot times r, right? Yeah, like we said, omega is v over r, so v is omega times r. Okay, these are two conditions, but note that they are conditions in the velocities. They are not conditions in the coordinates. The coordinates play a role in this, because it could be dependent on the position and orientation. However, we talk about velocities here. And so these are constraints. On the velocities, and there's a very fancy word for that. The fancy wording here is these are so-called non-holonomic constraints. So if you want to say what it is, you say what it's not, right? Because we do know what holonomic constraints are. Read the book, I think Heike is very clear about that. She talks about scleronomic or holonomic, and I don't know all the names by head, but there's the scleronomic has to do, it's not depending on time, or it is depending on time. And holonomic means it's in the coordinate space. But non-holonomic means it's not in the coordinate space, but it's a little bit more than that, what we're going to talk about in a sec. And who came up with the name? The originator of this is Heinrich Hertz. He was the first actually who started a theory on these constraints on the velocity level. And which makes sense, because Hertz was, of course, the scientist who was always busy with contact dynamics, and this is clearly a case which happens when you have contact dynamics. When there's this wheel, where we have this contact point here, touches the ground. In that contact point, we have zero slip, or maybe finite slip, if you are interested in really contact patches and what happens there in detail. That's all too much for now. We do just idealized problems, like we do rigid bodies. We do also pure rolling, so zero side slip. Okay, let's again look more closely. We now have defined what these constraints are. Like, now let's look again in detail. So let's redraw the picture, x, y. We draw our wheel again. So now we know what we talk about. We have this position. We have this velocity vector here, which we defined here as v. V is this x dot, y dot, v along, v perpendicular. We need the radius, of course, and we need to define what our rotational speed vector was, beta dot. And, oh yeah, of course, the angle of the wheel, phi, and the positions x and y. Maybe we don't need all the coordinates, but it's good to make the complete picture. Okay, so let's start with the first constraint. So that is, the first constraint is that this v perpendicular should be 0. Now v perpendicular, if we express that in these coordinates, that is this v dot, not v dot, that's the velocity vector v, and then the dot product with a vector which is perpendicular to the wheel, and that vector is of course minus sine phi cosine phi, right? That vector is directed along this direction, and if we take the dot product of this one with this one, we get this component, and that should be, that is, you can write it out, x dot, y dot, dot product with minus sine phi cosine phi, and then you say, oh, apparently that will be minus x dot sine phi plus y dot cosine phi, and that should be 0. So that's the first constraint. Now let's go to the second one about the rolling, pure rolling. So there we wrote that v along the direction of travel should be equal to beta dot times r. Okay, what is this velocity in the direction of travel? That's again this dot product of this vector, but now in this direction. So that's v dot product with, and that's simply cosine phi sine phi, right? And that for this one, if we write that out, for the dot product, I always try to write a thick dot. Okay, sine phi, or in other words, this v perpendicular is, and that is super easy, x dot cosine phi plus y dot sine phi, and that should be equal to beta dot times r. Okay, so this is one constraint, and this is the other one. Two constraints on the velocities, two non-holonomic constraints. For now, we're going to focus not so much on this one, on this forward rolling constraint. It's interesting because then you can keep track of how many revolutions you have with the wheel, etc. Or you can even drive the wheel by adding a motor to that. It's a bit of a strange coordinate actually, because it's a relative rotation, this rotation with respect to, with respect to the inertial world, right? And like this vector, phi is always about the vertical axis on the plane, where this vector is about, rotation is about a vector which changes. And there you already get a bit of a flavor of orientations with angles in space, that which we're going to talk about next week, and the week after that, and the week after that, and the week after that. So it's going to be a long period about 3D rotations and dynamics. But here you already see the flavor about rotation in space is about axes, and those axes change also. And we will see actually that in space very strange things happen. Okay, back to our problem. So for now I want to focus on this one, no side slip. So focus on no side slip. And you could also say like a skate, because then if we forget about, it's a wheel which is turning with rotations, then you could also say, no, this looks a bit like a skate, right? So let's redraw that again. So here we have again these coordinates, and now I draw this line, and I draw this wedgy thing which denotes a skate. So now this whole beta is not involved anymore. Then we have this velocity vector here, of course. We have our position x and y, and we have our orientation of the skate phi. And of course we want, this is not a nice phi. We want, of course, that this perpendicular velocity is 0. Now this perpendicular velocity we will give a name. So we decompose it in these two parts. So this perpendicular velocity, we will call it a slip 1. And here we have the forward velocity, and you can already guess, of course, that slip number 2 is going to be called, how did I don't define it? Probably like v in this direction minus beta dot r, or maybe the other way around. Hey, you know, with constraints, you can always change the sign or multiply it with a factor. Factor minus 1 is changing the sign. But for now we're not going to do that. We're focused on this one. So no side. So the side slip, that's actually what we defined now. So side slip is this S1, and it's a velocity. It's a velocity. And again, we can borrow that expression. This side slip S1 is then simply defined as minus x dot sine phi plus y dot cosine phi. And if we look at it, so this is a skate, I should say. And if we look at it, it's simply a constraint, right? It's a constraint in where we see the coordinates. We see not all coordinates here. We see phi, but some coordinates, and we see velocities. So you could say, in general, this S1 is an S1 of the coordinates and of the speeds. But it's more general. It's more specific than this general case because it is linear in the speeds. So this S1 is linear in this x dot I. And that's an important thing here. So for all the cases where we look at non-holonomic constraints, at least in the book and so on, we're going to talk about these constraints which are linear in the velocities. You can maybe think of constraints on the velocities which are non-linear, and by head I can think of something. For instance, if you want to add that kinetic energy as a constraint, I don't know if that's useful, but then that's quadratic in the speeds. But the physical interpretation, I don't know, and especially I looked it up in the literature also, and it's very hard to find a constraint expressed in the velocities which has a clear physical interpretation. But the Russians actually wrote some on that. Okay, back to our topic for today. Linear in the speeds. So we can write this S1 as some matrix times the velocities. X dot 1, well, I don't have a 1 here. X dot, y dot, phi dot. And then in front of this we have minus sine phi. I now use the shorthand notation, right? Cosine phi. And this is a 0. And then we write that as S1I times x dot I. But note, there is no comma. Meaning there is no dxi. It's not a partial derivative. Or let me say that again. S1I is not a partial Derivatieve. I will get to that in a second. Okay, we of course we will need our constraints not only on the velocity level but also on the acceleration level. So s dot, the side slip acceleration, you could say, yeah. So what is the side slip acceleration? Well, I keep this constant and I differentiate that. So then we have x double dot, y double dot, phi double dot, plus, and then I get all these mixed terms. So now I have to get with respect to x times x dot, well there is no x, with respect to y times y dot, there is no y, and then with respect to phi times phi dot, and there is a phi. So I get the sine phi is cosine phi, so I get minus cosine phi, phi dot x dot, and then for the second term I get minus sine phi, phi dot y dot. And this is what we call the convective term, right? These are these convective things. Okay. We could, of course, also write this as a bilinear product, right? Because it's always quadratic in the forward speed. And one way to do that is in this way. We take the velocities x dot, y dot, phi dot, transpose, then we get a matrix, and then we get x dot, y dot, phi dot. That's a way to write bilinear expressions. Then we have to fill up this matrix, and well, there are a lot of zeros in it because it only has to do with phi dot and with x dot and phi dot. So you could say, well, I only fill in this last column, right? So I get all zeros here. And then the only contributions I have here is minus cosine phi and minus sine phi. But, and of course we can write that in symbols. We can say s dot equals, and then what did we have? We had this non-Jacobian thing. S1I times x dot I, x double dot, sorry, plus S, yeah, and now we get 1I, comma, that's a real comma, because that was a partial derivative, times x dot I and x dot j. Now note, if you look at this, and note also that this is not symmetric in I and j. And actually this is what we say is the hallmark or fingerprint, print, not an S. How do I make a fingerprint? You have all these things like in lines. Oh yeah, you have lines. I don't know. Is this a picture of a finger? This is a bad picture of a. This is a bad picture of a fingerprint. Okay, again. So you could say fingerprint. This. Huh? It's a fingerprint of a non-holonomic constraint. Holonomic constraint. Okay. Now, and of course this you can form into one expression. I have to talk a little bit about this fingerprint hallmark thing. Why is it so difficult to draw a fingerprint? Oh, that shouldn't be so hard actually. So if this is your finger, then a fingerprint is just these concentric circles, right? And sometimes you have a line here and then you have other circles. It looks bad. Okay, I have to study on this, guys, sorry. For now, this should suffice. Oh yeah, if I put a nail there, you know it's a finger, you know what the top and the bottom is. Fingerprint. hallmark of the intermezzo, because this, you would say, why are you telling me this? Well, I'm telling you this because we have this expression. S is, what did we have? Minus x dot sine phi plus y dot cosine phi, right? Then if, suppose this is a derivative of a function, so we say suppose S is something like df dxi x dot I, then what is f? F of x. And that is the question. Or you could say, is this integrable? Is this an integrable function? Or is S x I x dot I an integrable function? So does it have a primitive? This primitive f. Well, we can easily check that. Because we just write the partial derivatives and then we integrate, right? So what is the partial derivative? So df dx, is, well, that's the term for the x dot here, right? So that should be sine phi. df dy is cosine phi, and the df d phi is 0. Okay. Now suppose I differentiate it with respect to phi, then I get cosine phi. So I have now the mixed derivative to x and phi, but if f would be a function, I can also take the derivative with respect to phi and differentiate it with respect to x. So if I do df d phi dx, but that turns out to be 0. Now how can 0 be equal to cosine phi? That's only for one case, and that is when phi is pi over 2 plus k pi or something like that. So in a very special case, so not as a function, not in generality. So if f exists, then they should be equal. Equal. But they're not. Ergo, f does not exist. And there's also another way. If you could say, if I try to integrate this s, the value of the integral depends on the path that I take. And usually with integrable functions, that is not the case. But yeah, with non-integrable functions, you get different results if you take a different path. And we took different paths here because, well, here with differentiation, but here if you take the integral path you take is the integral path with respect to phi, and here is if you take the integral path with respect to x, and then I get different results because here I get sine phi and here I get 0. So what's going on? Well, it's non-integrable. Okay. And this non-integral we then say non-integrable. That is then this non-holonomic. Mic, that's a C. Okay. Now we want to have the equations of motion, EOM. Equations of motion for a non-holonomic constrained system. Yeah, and of course the start is again with our virtual power expression. Virtual power expression, and it's a little bit boring in that sense. Mij x double dot. It's our most powerful, or almost, nearly, almost our most powerful instruments. Should be 0 for all virtual velocities which fulfill the constraints. And the constraints are, in this case, we have non-holonomic constraints. Of course, you can do a mix of holonomic and non-holonomic, and that is in the book, I think. But for now, I only want to see what is the impact if we do non-holonomic constraints, because we have the other one, and then the mix is just adding those parts, right? If you can do it for one, and you can do it for one more, you can do it for infinite. Okay, non-holonomic constraint is, I write this as capital SK, and I immediately know they have this form, SKI x dot I is 0. That is our constraint. Now if we want to incorporate that, then we have this virtual one, and again this remains constant, and if my virtual velocities is 0, then again times the Lagrange multiplier lambda k, and we then add that to our virtual power expression. We put a star there, we get Fi minus Mij x double dot j, virtual velocity I, and then, yeah, this is just a sign convention, minus, it has to do with power supplied or subtracted through to the system, through or to. SK is 0. Yeah, let's write that again. So we get Mij x double dot j, virtual velocity I. Now I write out what this guy is. This is my SKI, virtual velocity I is 0. And now everything is in, it's for all virtual velocities now, as long as they're not 0. And then we get I equations, right? And these I equations are simply, oh, don't zoom, are simply our equations of motion, right? Fi minus Mij x double dot j minus lambda k ski is 0. And of course we have also our constraint. We have our ski, which we have to differentiate x double dot I plus ski comma j x dot I x dot j is 0. And with these two sets of equations form our equations of motion, which we then nicely write in this mixed form, right? It's mixed. So we have Mij. We have, yeah, it doesn't matter, with the indexes SKI. Yeah, I had I as an index. X double dot j lambda k, and then on the right hand side I have my applied forces Fi. Then I have my constraint in the velocity, in the accelerations, Sk, but we have a j here, so this becomes a j, that index. And then minus Sk, well, L comma m, to be super clear, x dot L, x dot m. Okay, now that's easy. So again, and then we can solve for x double dot j and lambda k given the time, the positions, and the velocities. And then of course we can find the approximate new velocities, the new approximate positions, n plus 1 is the old one, plus the numeric integral, and I like to write it like this, of x dot n dt, and the approximate new speeds are the old speeds plus the numerical integral of x double dot n dt. Now you will see, that in general these velocities now, these new velocities, do not fulfill the constraint. So that x dot n plus 1 does not fulfill this ck I x dot I is 0. And note the n plus 1 and the I are different indices. N plus 1 means a step, and I is just the tilde, and with the tilde now I mean the approximation. However, that is easily solved. Easily solved with a one step, because it's a linear problem, Gauss-Newton process. Gauss-Newton process. Think of the coordinate projection method. Coordinate projection method from, what is it, chapter 15. Okay, how does that go? And let me write the algorithm again. So, well, you assume that the real position, the real correct ones, is the approximate ones plus a small increment, delta xe. So this is the, and then if we want to have, of course, that ski times x dot I. Why do I write these vector things? It's so stupid. Get rid of those. We're doing indexes. Oh yeah, because of this. Step n to n plus 1. Okay, anyway, this should be 0, right? And then we substitute this in this equation. What do we get? We get ski times r tilde. That's actually, of course, the error we have, right, in our problem. Plus, and then we get, the Jacobian, which we already have. So that's the beauty of the linear problem, is 0. That is what you call the error in sk. And then we can easily say, oh, delta xi is, what did I write, minus, oh, I used this Moore Penrose notation. Remember, that was the Moore Penrose inverse times ski x dot with a tilde. What did I do? Tilde dot. I did tilde dot. Remember, tilde dot I. And this is a Moore Penrose pseudo inverse. Or you could also in MATLAB do, what is it, the backslash, and then you do ski backslash. Yeah, it's now a very super strange mixed notation. It's MATLAB. And then of course you increment, and then you're ready. If you then add this increment, then you already have in this one step the correct position. Okay. Yeah, and now I want to use the last 5 minutes to talk about an example, and it has also a close relation to the homework problem. Example. And the example is the Chaplin sleigh. And Chaplin is a name of a person. So Serge Chaplin, who was he? Well, he lived from 1869 to 1942 in Russia. 1942 is, I probably know why he died, somewhere in Stalingrad or Leningrad or horrible. Anyway, his teacher, he was a teacher of, no, not his teacher, he was the teacher. Stupid me. He was the advisor, let's say, teacher of Sadov. And then you think, who the hell is Sadov? Well, Sadov was the designer of the Sputnik. And then some of you may say, what is the Sputnik? Is there some vaccine? Well, yeah, actually it's a vaccine now. But what used to be the Sputnik was the big astronomical, astrophysical, was it really astronomical? Success of the Russians. It was the first satellite. What was it? It was this bleep thing with these antennas, and it was saying beep, 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 and then everybody got totally scared in the US and all over the world, and it was circling around the Earth. So here we have Earth. Oh my God. Circling around Earth, and beep, 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 and everybody thought, oh, the Russians are already in space and we are way behind. That was Sputnik. Okay, what is this Chaplin sleigh? Well, it's just one rigid body with a center of mass, and then at the distance a behind the center of mass we have this sleigh. So we have again phi positions x, y. This distance I call a. And yeah, again, for this you can write down what the problem is, right? So if this is point A, we have here velocity of point A, and of course we want this velocity at A perpendicular to be 0. So VA perpendicular should be 0. That's our constraint. Now how do we determine VA? Well, VA is VC plus V of A with respect to C. And then with the geometry we can define, with the orientation we can take dot products, and then we can find out what the expression is. Okay, how many degrees of freedom do we have for the system? Well, of course we have coordinates are x, y and phi. And of course the speeds are x dot, y dot and phi dot plus one constraint. So the degrees of freedom in the kinematic space is 3, but the degrees of freedom in the velocity space is 2. So in xi, so in the coordinates, I have 3 velocity, degrees of freedom. Whereas in the speeds, velocities, I have only 2 degrees of freedom. And you can also have another look at this, like, okay, if I have a skate, I can put anywhere on the plane. I just pick a spot, right? Just say here, I can put my skate, and I can put it at any direction. For instance, this direction. So, boing, your skate is there, perfect. And your body, of course, the whole body. However, the mobility, that means the 3 degrees of freedom, any position, x, y, any orientation. However, the mobility, how can it move, how can it change position from one to the other, so the velocities, the mobility in the thing is, well, you could say it can move freely, can have a velocity along this line, so it can have some local velocity here. How are we going to donate that? If we say v, that's super, well, no, let's write it. It can have a velocity v, and it can have some rotational velocity, of course, but the rotational velocity must be such that the velocity here is, of course, the lateral velocity is, of course, 0, right? Well, here we already have a velocity which has no component, so this should be then the pole of the motion, so we can say, oh, there's also like an angular velocity, omega. So you could parameterize these two unconstrained velocities with the velocity along the line of the skate and the rotational velocity of the body. Anyway, this shows that there is this difference in these dimensionality of the degrees of freedom between the coordinates and the velocities. How do the equations of motion look? Well, that is actually super simple now, because we have our constraint, right? So v perpendicular should be 0, and then I said, oh yeah, how does that work? That was this velocity. Oh, let's draw it again. Where is? So coordinates, we have this body here, center of mass, this line, this point here where the skate is, A, and distance A from the center of mass. Here we have the center of mass with x, y, and of course this angle phi. Then the velocity of A is the velocity of point C, which is the center of mass, plus the relative velocity of A with respect to C. In this case, it's sort of super simple. VA is then, well, VC is just x dot y dot, right? Then the relative velocity of this point with respect to that, well, if there's an angular velocity like this, phi dot, then here we have a component, right, which is called phi dot times this distance A. And then we just, this is in the local coordinate system. And then we have to transform that to a global coordinate system, but we know what the orientation of the body is. So we could say plus, well, in the x component we get a phi dot sine phi, right? And in the y component we get minus a phi dot cosine phi. Then this we have to take with this perpendicular distance, so we have apparently some vector E, which is perpendicular to the skate. So this vector E is, we could say E perpendicular. And the E perpendicular is, what is it? Minus sine phi cosine phi. And then our expression for, don't zoom, our expression for V perpendicular is of course the E dot perpendicular dot product with this VA, or in other words minus sine phi cosine phi times, and then here I get x dot plus a phi dot sine phi, and here I get y dot minus a phi dot cosine phi. Well, then we have to multiply this out, right, and then we get V perpendicular is apparently, now what do I get? Minus x dot sine phi minus a phi dot sine squared phi plus y dot cosine phi minus a phi dot cosine square. Oh, those two go together, right? So we get minus x dot sine phi minus plus y dot cosine phi minus a phi dot squared. And that is our non-holonomic constraint. So in other words, this sk equals now minus x dot sine phi plus y dot cosine phi minus a phi dot squared. Why do I say phi dot squared? Because sine squared and cosine squared. Stupid. Of course not. Just phi dot. Okay. And why do we have this term now? Yeah, because the skate is not at the center of mass, but is distance a from the center of mass. So we have this additional term. And of course it's in the direction exactly perpendicular to the skate. So we have just this a. Well, it's now super easy actually, so we have to do s dot k, that is the constraint which we have to add, minus x double dot sine phi plus y double dot cosine phi minus a phi double dot, yeah, and then plus all these convective terms. Now I don't want to make errors, so we get minus x dot cosine phi phi dot, and then again minus y dot phi dot sine phi. Yeah. Then we can put that, of course, in the big matrix vector thing for our equation of motion. So we get our differential algebraic equations. Well, it's not completely correct. It's because the algebraic we already formed also to a differential equation. So it would be if you keep this and you write down the equation of motion. But anyway, this is nitpicking. If somebody's interested, I can talk about it more in the questions and answers after this, after the beep, yeah. So it's two parts, of course. It's the mass matrix, and these are the coordinates, x double dot, y double dot, phi double dot. We have only one multiplier, lambda. Then we put in this Jacobian thing here and here. So we get minus sine phi, cosine phi, and what is it, minus a, yeah. And here we get also the same, minus sine phi, cosine phi. Isn't mechanics beautiful? It's just like bookkeeping, right? It's not hard. Fx, Fy, and m, so this is all at the CM, the center of mass forces. And then this term we have to put on the right hand side, minus x dot phi dot cosine phi plus y dot phi dot sine phi. And then we close the bracket. And of course, we still have to keep in mind, and that is for the numerical integration, and for the velocities all the time we have minus x dot sine phi plus y dot cosine phi minus a phi dot is 0. We have to keep track of this, and this is what we then use for our constraint stabilization. You can easily set up the simulation, calculate the stuff, correct it with this constraint, and then you can see the motion of the skate. Well, that's actually the topic of this week's homework. So for now, we start the Q&A in Zoom at, what is the time? 9:54. So well, let's start at 10. Then I have a 5-minute break after this stressy startup, and then we continue. So yeah, I can stop this. A2 playbacks. Okay.